Hi folks, welcome to the 2021 edition of the Chapter 4 Concept Roundup for Math 621B. This year the curriculum's a little bit different. It deals with some stuff that used to be in 521B, so we've got this slightly amended version of the video. In the video description down below, you'll find timestamps for each of these 7 topics that are on here. You'll also find links to PDFs of a practice sheet, PDF of the full worked solutions, and also a link to the video of the worked solutions to those practice questions. So there's a bunch of stuff there to help you learn the material. So let's dive right in. The first thing we're going to look at is angles in standard position. So angles in standard position are measured counterclockwise from the positive x-axis. If you were to draw 70 degrees, you'd make your axes, you'd start at the positive x-axis, and you'd go 70 degrees counterclockwise. I want to show that direction with the arrow. 450 degrees. So now we can break out of 360 degrees. We can go 360 and another 90 would get us to 450 degrees. That's an angle that ends up at the same place as 90 degrees. It's coterminal, we could say, with 90 degrees. If we have a negative angle, then it's going to go clockwise. So negative 120 degrees is going to look something like this. A couple of things to mention while we're at it is that there's this idea of a reference angle. A reference angle is the smallest angle that is made with the x-axis, and it's often denoted theta r. Next thing to talk about is something that was in 521B. It's trig values in standard position. So if you have some angle like this, and there's some point xy on it, and you've got an angle in standard position like this, theta, we're going to define the cosine to be x over this distance here, which we call r, or the radius. Now you can also think of this as building a little right triangle. There really is Pythagorean stuff happening here. And that r, if we went with Pythagorean theorem, the height of this would be x, the width would be y. R squared is x squared plus y squared. Or r is root x squared plus y squared. So the cosine is going to be x over r, the sine's y over r, and the tan is y over x. This allows us to define these trig ratios for angles that go beyond just what happens in a triangle. And let's just talk about rotations when we're talking about angles. So as an example, if we've got the point 3, negative 5 that lies on the terminal arm of some angle in standard position, sketch and find sine, cosine, and tangent. So if they're going to tell me what the point is, I am going to sketch that point. So 3, negative 5 might be down here. Okay, and we're talking about a terminal arm that goes to here. And we're talking about the angle in standard position. So again, it's measured from the positive x-axis. And I know that cosine is going to be x over r. And sine is going to be y over r. And tan is going to be y over x. Okay, those are our definitions. I'm going to stick with them. I do have to take a second off to the side and figure out what r is. So r is the square root of x squared plus y squared. Or r is the square root of 3 for x and negative 5 for y. And it's all squared. When I put numbers into a formula, I sub them in brackets. Okay, so let's figure out what's happening here. That would give me r is the square root of 9 plus 25. And I'm going to leave this value exact as root 34. Yes, you could get a decimal approximation in your calculator, but it's never going to be more perfect than it is right now. Once we have that, well, we can write down what cosine is. It's x, so the x value was 3 over root 34. The sine is y, which is negative 5, over root 34. And the tangent's going to be negative 5y over x. Tan's the easiest one to find. Doesn't rely on r. You can optionally rationalize those denominators for sine and cosine. And the way that we do that, and this is harkening back to 521b is just multiply top and bottom by root 34. So that you get this thing. The reason that we often like this is that it makes more sense to divide by 34 than by root 34. But I'm not too picky about this at this point. The main thing is that we get a reasonable value. So negative 5 root 34 all over 34. Okay, really either one of these statements, this one or this one, are okay. I guess the one with the rationalized denominators a little nicer. The next thing we're going to talk about is radian measure. I mean, it says right here, an angle which subtends an arc the same length as its radius is called a radian. So here's the definition of a radian. If you have a radius on this circle of r, and another one here, if this crust piece here, the arc, is also r in length, so if you have exactly as much radius as you have crust, then this angle is defined as 1 radian. Okay? And the basic conversion, the most important one, is that pi radians is 180 degrees. Now, we consider radians to be the natural angle measurement system. If you see a degree sign, we're in degrees. At this point, if you see no unit, then assume that we are in radians. Some common angles that you'll run into 2 pi, which is 360 degrees. You'll run into half of pi, or pi over 2. That'll be half of 180, or 90. 1/3 of pi, so 1/3 of 180 is 60. Pi over 4 would be 180 divided by 4, so 45. And lastly, pi over 6 is going to be 180 divided by 6, or 30 degrees. These are our common angles. If you want to convert using some conversion factors, if you want to go 2 degrees, we're going to multiply by 180 over pi. If you want to go to radians, we're going to multiply by pi over 180, because those two things are equivalent. So I'm going to show you how I like to convert. I like to think of these in terms of the common angles if I possibly can. So if I see 3 pi over 4, I think, oh, pi over 4 is a 45. So I've really just got 345 degrees. In degrees, this is 135 degrees. Alternately, you could have used a conversion factor. You could have done this. I guarantee you, if you work that out, you'll get 135 degrees. But it's going to be more laborious. You'll have to divide out those pi's and go 540 divided by 4 gives you 135. So again, in the next one, I'm thinking that's 7 pi over 6's, so that's 7/30s. Hey, yo, that's 210 degrees. This is 3 pi over 2, so that's 3/90s. Okay, that's 270. And again, if you wanted to use a conversion factor, you could. D, we're kind of out of luck. That's not got anything to do with our common angles. So I think here we're going to have to suck it up and actually multiply by 180 over pi. When we do that, we're going to get about 298 degrees, and you would do that in your calculator. Looking at some of these other ones, 210 degrees, again, I'll try and relate it back to my common angles. So 210 is 7 30-degree angles. So that means it's 7 pi over 6's, or 7 pi over 6. Negative 225, that's going to be negative 545 degrees. So it's going to be negative 5 pi over 4's, or negative 5 pi over 4. And again, if you wanted to, you could use a conversion factor and it'll get you the exact same thing. Though if you throw that in your calculator, there's a good chance it will give you a decimal approximation instead of an exact value. And depending on the question, you may be expected to do an exact value. 120, I would think of that as just 260s. Okay, so that's 2 pi over 3's, or 2 pi over 3. And again, we have one here that defies our common angles, so we're going to have to use this conversion factor right here. We multiply by pi over 180 degrees. You can see the units divide out, the degrees. And you do that in your calculator, and you'll get about 1.29 radians. And that makes sense, because 1 radian, I guess I forgot to put it here, 1 radian is about 57 73.3 degrees. So 73.9 degrees is going to be bigger than 1 radian. Unit circle. Here we go. So the unit circle is a circle with a radius of 1. And the nice thing that that does is normally we have this definition that cos theta is x over r, right? And sine theta is y over r. But if we cut down the radius to just be 1 unit, then we'd have x over 1 and y over 1. If we go with a radius of 1, then the x values everywhere on the unit circle are going to be the cosine values, and the y values are going to be sine. So that's why it says here, every point on the circle has coordinates cos theta for x and sine theta for y. Okay, so if I go to some point here, it's going to have these coordinates, whatever the angle is, as long as I have a radius of 1. Now the easiest points to pick off are these ones, right here, right on the poles. And I think those are worth, I don't know if the right word is memorizing, but at least understanding what's going on at those points. So what does it tell you then? Well, it tells you if you had, say, 90 degrees, then you'd be having a cosine of 90, that is that x value of 0. And the sine of 90 is that y value, which is 1. So that's kind of helpful. You could check those things in your calculator. They are indeed true. It also tells us a few other things. It lets us know where each ratio is positive. Positive. Okay. So in the first quadrant, they're all positive, sine, cosine, and tangent. In the second quadrant, only sine is positive because the y values are going to be positive. In the fourth quadrant, only cosine is going to be positive because the x values are positive, but the y's are negative. And in the third quadrant, both x and y are negative, but that means y over x is going to be positive. So we learn which ratio is positive in each quadrant. Now, you can get a big unit circle that has a bunch of common angles on it, and I put one on the last slide. But we're typically going to work with just the quarter circle because it takes a long time to make a full unit circle with a ton of angles in it. But all the special values that we learn come from a couple of important triangles. So I'm just going to take a second here and run through where some of these values come from. If I imagine an equilateral triangle just like this, okay, it would have 60 degrees here, 60 degrees here, 60 degrees here, and let's give it side lengths of 2. I could split that down the middle, and I would now have a triangle that looks like this. 60-degree angle here, right angle, 2. The bottom would be half of that 2, so 1. I'd also have 30 degrees here. And from Pythagorean theorem, we could figure out how big this other leg is. So 2 squared would be equal to 1 squared plus, I don't know if we want to call it b squared. We'll find out that b is root 3. That gives us some exact values. If I go from 60, then the cosine from SOHCAHTOA is adjacent over hypotenuse. So the cosine of 60 degrees, let me write that with a 60, is 1 over 2. Okay. The sine of 60 degrees would be opposite over hypotenuse. And the tangent of 60 degrees would be opposite, which is root 3, over adjacent, which is 1. I can also relabel this triangle with respect to the 30 degrees. And then the cos of 30 degrees is going to be, well, now this is my adjacent, the root 3 over hypotenuse. The sine of 30 degrees is the opposite over the hypotenuse. This is kind of from grade 10 trig. And tan 30 is going to be opposite over adjacent, which can be rationalized as root 3 over 3. So that gives us a bunch of exact values just from this sort of imagined triangle. Let's do another one of these imagined triangle. I could imagine a isosceles right triangle. Okay, something like this, which has legs of 1. And from Pythagorean theorem, you could show that, therefore, it would have a hypotenuse of 2, of root 2, rather. From that, you can show that the cosine of 45 is adjacent. If I went from here, adjacent over hypotenuse, which could be rationalized as root 2 over 2. The sine of 45 would be opposite over hypotenuse, which again could be rationalized as root 2 over 2. And the tangent of 45 is going to be 1 over 1, or just 1. Those are some values that we want to know. Okay? And we can learn them straight from the triangles and keep the triangles together all the time. The question is how best to organize them. And that's really a matter of taste. So here it says, creating a full unit circle is cumbersome. You can organize your trig values any way you want. I like a unit quarter circle. So here's what I do. I make the arc of the quarter circle, and I talk about the important angles that are in it. So that would be 45. Here's 60. Here's 30. And I'm just going to draw what those angles are in degrees and radians. So 0 degrees makes 0 radians. 30 degrees, we already said that's pi over 6 radians. 45 is pi over 4. 60 is pi over 3. And 90 is pi over 2. Already, it's helping us convert between the two, as long as we've got that sort of big idea that pi radians is 180 degrees. On this unit circle, there are some easy points to get. There's this point, 1, 0, because it's got a radius of 1. There's this point right here, 0, 1. And then there are the rest of them. Okay. And we already showed what the sine and cosine of 60 degrees are. So I just want to show you a little trick for how to write this quickly. They're all over 2. Okay. And all I do, I think of the Jackson 5 tune, ABC. It's ABC as easy as 1, 2, 3. Here's what we do for x's. It's root 1, root 2, root 3. Okay. And same for the y's. Root 1, root 2, root 3. I'm not going to sing the song because YouTube is very particular about its copyrights. So then we know a way to organize all the cosine values. If I want to know the cosine of 60, bam, I just look at the x value of 60 degrees. If I want to know the sine of 45, bam, I look at the y value when I have an angle of 45. X is cosine, y is sine theta. Y over x, I'm going to put this in a different color actually. I'm going to do it in red. Y over x is tan theta. But it's annoying to have to figure that out all the time. So let's just put it on the exterior of this whole quarter circle. So 0 over 1 would be 0. 1 over 0 would be undefined. Anything divided by itself would be 1, so the tan of 45 is 1. And again, we showed that already, that the tan of 45 degrees is 1. And the other two you might want to just memorize. 1 over root 3, which you can also write as root 3 over 3. And this one's root 3. Knowing these values is kind of the key to doing a bunch of questions that don't involve your calculator, that involve exact values. It's also worth noting that we're still dealing with this all, sine, tangent, cosine. And for angles that end up on the axes, it's also worth remembering that those values are real easy to deal with. They're going to be 1, 0 there. 0, 1, negative 1, 0, and 0, negative 1. Again, we're being told about sine and cosine values because x is cosine and y is sine. So we can use reference angles and ASTC, that's the quadrants, to find sine, cosine, or tangent of any multiple of a special angle. That means 30, 45, 60, and 90 degrees. So let's do that. Over here, I got a handy-dandy little unit quarter circle. And I did put my tangent values in green in this one. So if I want to find a trig value without my calculator, here's what I do. I sketch the angle in standard position, because right here it tells me I want the sine of 120. There's no doubt what the angle is. Okay, so 120 degrees looks like this. Its reference angle is this little one here. So how big is that? Well, it's got to be 60 degrees. 120 and 60 make 180. So now what do? I head over to 60 degrees, and I'm going to look at the y value, because we're talking about sine. Y is sine. And it tells me it's root 3 over 2. That's sort of step 2. It says use the table, use the quarter circle. I've done this before with a table instead, so use a quarter circle, or whatever you use to organize your trig values. And lastly, decide whether it should be positive or negative. So in this quadrant, right here, second quadrant, is sine positive or negative? It's got that big S there. It's positive in this quadrant. So I don't need to write the plus. I'm just making the point here that it's definitely positive. Let's try this for a couple of other ones. So 7 pi over 6. If you want, you can turn this into degrees. I'm just thinking 6 pi over 6 gets me to there. Oh, and it wants to make a nice circle for me. And it wants to do other fancy things. Let's try this again. There it is, drawn to 7 pi over 6, or 210 degrees. The reference angle is going to be pi over 6. That's going to happen anytime you have like an over 6. It'll always be a reference angle pi over 6. So let's check it out. At pi over 6, boom, this is what we're interested in. Okay. We want the x value because it's cosine, so that's root 3 over 2. And now we have to decide, in this quadrant, is cosine positive or negative? And you can see here, it's positive in quadrants 1 and 4. It's negative back here. So the answer here should be negative root 3 over 2. Lastly, tan of 7 pi over 4. So again, if you want, you can call this 315 degrees, or 7 times 45. But I'm just thinking, oh, there's 2 pi over 4, 4 pi over 4, 6 pi over 4, 4 pi over 4. Okay, that is the angle 7 pi over 4. The reference angle is going to be this one right here. It's with the x-axis, not with the y-axis. So get a reference angle of pi over 4. And now I have to look, okay, pi over 4 is right here. Maybe I need a new color. It's right here. And I'm looking for the tan value of that, which is 1. Okay, so apparently tan of 7 pi over 4 is 1. And last step, ask yourself, in that quadrant, is tangent positive or negative? It's positive in quadrants 1 and 3. It's negative in this quadrant. So that's how we find these values. That brings us to these reciprocal trig ratios. So there are sort of the primary trig ratios, and then there are the dark trig ratios of cosecant, secant, cotangent. Generally, I think you should try and get to primary trig land as quickly as you can. But there are the definitions. Cosecant is 1 over sine, secant's 1 over cosine, cotangent's 1 over tangent. Each one has a co-buddy. If I want to find secant of 30, I know that the secant of 30 is just 1 over the cosine of 30. Now, cosine of 30 is not that hard to find. Cos 30, let's see, it looks like this. It's going to have a reference angle of 30. Oh, let's just find it over here. 30 degrees. The x value is root 3 over 2. Okay. So the cosine of 30 is root 3 over 2. It's in quadrant 1, so it's positive. The reciprocal of the cosine of 30 is just going to be 2 over root 3, just the flip of it. So we did not flip the angle. We found the cosine, and we found its reciprocal. If you want, you can rationalize that. So by multiplying by root 3 over root 3, you get 2 root 3 over 3. That's fine. I'd think this is all right, and this is all right. Either one's fine. So anytime you're faced with these reciprocal trig ratios, I think you should just turn them into a regular one. So this is 1 over the tangent of 3 pi over 4. Notice I didn't flip the angle, right? And you never would have flipped the angle for 30 degrees. Sometimes weird stuff, though, happens when people do radians. So let's think about that. Tan of 3 pi over 4. Can I figure that out? 3 pi over 4. Let me sketch it. That's 135 degrees, or 3/45s. And I'll just zoom in a little bit here. Okay, the reference angle would be pi over 4. Okay, let me check this out. Pi over 4, or 45. There we go. Here's the tan value. So the tangent would be 1. And in this quadrant, tangent would be negative. So what I get here? I get 1 over negative 1. Or in other words, just the reciprocal of negative 1. And in this case, the reciprocal of negative 1 is still just negative 1. We did have to consider that flipping over because if it had been any other number, we might have run into trouble. Okay. So find the trig value for the primary trig ratio and then just flip it. Okay, that brings us to a topic that really could be put in anywhere. It doesn't have to be necessarily trig specific, but it's just this way of showing domains. So sometimes people find this kind of notation confusing. Like, why don't we just write it as 0 to 2 pi? That would be kind of nice. And interval notation sort of does that. We do have to deal with the fact that in that statement, 0 is included and 2 pi is not. So interval notation is a way of showing domain or range where you just show the starting point and the ending point. So if I wanted to talk about this domain right here, 0, it goes from 0 to 2 pi. Okay? And the 0 is included, so it gets a square bracket. The 2 pi is excluded, so it gets a round bracket. This is something that's done a little differently around the world, but in North America, this is the convention. The problem with this notation is that you might mistake it for a point. So sometimes people will do this. X is an element of, or belongs to the set of, numbers from 0 to 2 pi. It's two ways of writing the exact same thing. If you did it as a number line, no, it's from 0 to 2 pi. 0 is included. 2 pi is not. So it's from 0 to 2 pi. Infinity is never included. So if I did this one, x is greater than or equal to 3. So if I had a number line here, let me think about this. There's 0. Here's 3. And we're talking about numbers that are bigger than or equal to 3. So 3 all the way up. That would be from 3 all the way to infinity. Infinity is just an 8 lying on its side. And 3 is included, and by convention, infinity is not, because it's a concept. It's not a number that you can actually arrive at. Again, if you wanted to, you could write this, though it isn't always done. That brings us to sort of the key skill of the chapter, which is solving trig equations. Trig equations give you a set of conditions, and then they ask, like, what are the possible angles? That is the key idea of a trig equation. And we're going to split this down into 4 sections. The first one's about solutions that are just in the first positive revolution. This is the most important of the skills. So here's our first trig equation. We want to find what angles have a cosine of negative root 3 over 2. And here's the 4-step process. I want to find theta ref. That's either going to happen by using the quarter circle, okay, quarter circle, or inverse trig on your calculator. Now you won't necessarily always have your calculator, so when we can use the quarter circle, we will. Use ASTC to sketch, so that means that we're going to decide on where it's positive and where it's negative, determine the angles in standard position, and write the solutions. I kind of think of it this way. So I want to find my reference angle. That's when I look at just the number, cosine of root 3 over 2. Now, cosine is x values in the quarter circle. Where do we have an x value of root 3 over 2? Oh my, right here. Okay, which means that we're talking about a reference angle of 30 degrees. That's how far it is from the x-axis. The next thing we're going to do is choose some quadrants. So notice here that the cosine is negative. Here's where we'll deal with the negative. Cosine's positive in this first quadrant, so it couldn't be there. Cosine's positive in the fourth quadrant, so it couldn't be there. It could be in either of these quadrants, though. And so now we know the reference angle and we know the quadrants. Now I can make a sketch, a non-terrible sketch of my answer. Reference angle of 30 degrees in the second quadrant and in the third. Once I have that, it's not too bad for me just to write the answers. I think I can figure out what this angle is just by going, oh, that one is 180 minus 30 degrees, or 150. This one over here, we've got 180 plus 30 degrees. And we're not going to generalize and say, oh, it's always one's minus and one's plus. We're just going to say, wherever those sticks land in my drawing over here, those are the places that the solutions are. There are 2 solutions, and we're done. So here we go. We have sine x is root 3 over 2. What's changed here? We're now in radians. Radians. Okay, so same sort of thing, though. We're going to find the reference angle. Okay, so where is sine root 3 over 2? Sine is y values. Here's a y value of root 3 over 2. That means we're talking about this angle right here. And I'm going to write it in radians, pi over 3. Next, I'm going to choose my quadrants. So if you're finding that you're making this a one-step thing, there's probably a little more to it. Check it out. Sine is positive here. That's positive root 3 over 2. So we could be in this quadrant or this quadrant where it says sine is positive. Moving on, let's sketch our solutions. So pi over 3, or about 60 degrees, could be in first quadrant, could be in second quadrant. And so those are the 2 possible angles that are going to give us this sine of root 3 over 2. This question is just asking, what are the possible angles? So one of these, I might have used theta in the last one, but x, theta, whatever variable that you have, doesn't matter. One of them is pi over 3. Okay. And then there's this one over here. How are we going to figure that out? Well, if it were in degrees, it would be less than 180 degrees. It would be 60 degrees less than 180. Here, if we do this in radians, 180 is pi, and it's pi over 3 less than 180, or pi over 3 less than pi. We just have to subtract those. And to subtract fractions, you need a common denominator. So that would be 3 pi over 3 minus 1 pi over 3, giving us 2 pi over 3. Alternately, you can do this whole thing in degrees and switch at the end, but it can be kind of cumbersome, and you don't get more used to working in radians that way. If the question's given in radians, the final answer should be in radians. Okay, so let's try another one. Tan x equals 2. So I've got to find my reference angle, and I look on my unit quarter circle. I don't see a 2 here at all. Now, if this were sine or cosine equals 2, there would be no solution. But this one here, we can actually operate on. It's just that the quarter circle doesn't have every possible value on it. When you can't find the theta ref from the unit quarter circle, what you're going to do is go inverse trig of the absolute value of whatever number you have. So inverse trig of whatever this constant is. So to find the reference angle, we'll go inverse tan of 2. Okay? And I have to make sure that my calculator is in radian mode, so let's head over. I'm on a TI-84 emulator called Calculate 84, which is very good and very free. I'm going to check that I'm in degree mode, so I'm going to pop that over to radian. And then I'm going to go inverse tan of 2. And it's going to tell me 1.11. That's my reference angle. Once we have that, we can just operate as normal. So I'll say, okay, what quadrants might I be in? Let's see. Tangent is positive in this quadrant and this quadrant. Let's make ourselves a picture. Don't get too hung up on how big 1.11 is. It's a little over 60 degrees. But we can just put it, as long as we're in the right quadrant, any rough sketch is fine. Make sure that those reference angles are with the x-axis, though. And now we're going to write our solutions. So the first one is pretty straightforward. It's going to be x is 1.11. And the other one is going to be this, 180 degrees, or pi, plus 1.11. So 3.14 plus 1.11 makes 4.25. And those would be our two angles that give you a tan of 2 in radians. So if it's not on the unit quarter circle, you're probably going to go and use your calculator. Here comes one last equation that's in the first positive revolution. It's still in radians. It's annoying, though, because it says secant x. So remember that secant is 1 over cos x. Let's just write it that way. So it means the same thing as saying 1 over cos x is 5, or 5 over 1. Once we have it written that way, you can just flip both sides. Now, you can rearrange it differently if you want. You can multiply both sides by cos x, then divide by 5. You're going to get the same result. Cos x is 1 over 5. Okay? And at this point, we can go through our regular stuff. Now it looks like a regular equation. Reference angle is going to come from inverse cos of 1/5, because I don't see 1/5 on that unit quarter circle. I'm going to go to my calculator. Inverse cos of 1/5 is 1.37. I write it in, and now I'm ready to choose my quadrants. Okay, ASTC. Notice here, cosine is positive. You can just operate from this version of the equation at this point. So cosine is positive in quadrants 1 and 4. Let's draw ourselves a little picture of the answer. Won't get too hung up on exactly how big 1.37 is. And then we just talk about what those angles are in standard position. So this one is just 1.37. And this one would be 2 pi minus 1.37. Now you can just throw that in your calculator, and you'll get 4.91. Those are our two solutions here. The next thing we'll look at is general solutions. So really, if I say, like, where is sine x equal to a half? There's this angle of 30 and this angle of 150. But if I don't restrict the domain, those also have an infinite number of coterminal buddies. Like, it could be there, or I could be talking about this one. So we can't write down infinitely many answers. That would be ridiculous. But we can make an expression that represents all the different answers. And the way that we do that is just find the answers that are in the first positive revolution. I think anyways, that's the easiest way to do it. And then just add 2 pi n, or 360 degrees n if it's in degrees, to each solution, where n can take any integer value. That means that you're saying that it's that initial solution plus every revolution that sort of ends in the same place as it. Okay, so let's try one here. We got cos x is root 3 over 2. Same stuff. Maybe we're getting a little faster at doing the basic solutions. Reference angle. I'm looking at here, looking for an x value of root 3 over 2. Reference angle is going to be, I'm going to do this one in radians, pi over 6. I'm going to choose some quadrants. Okay, it could be in either of those. I'm going to draw this. So that's going to be pi over 6 and pi over 6 here. And so those final solutions that we'll get are pi over 6 and this one over here, which is going to be 2 pi minus pi over 6, okay, or 11 pi over 6. Those are the initial solutions. To say that it's a general solution, all we need to do is say plus 2 pi n on each of these, okay, where n is an integer. So think if you put the integer of 1 into this one here, you'd get pi over 6 plus 2 pi, or 13 pi over 6. That would be this angle. That would get you right back to the same place. If I put 1,000,000 in for n, then I'd get pi over 6 plus 1,000,000 revolutions. But it would still get me back to the same place. And it would still solve the equation. The reason you can only put in integer values is because you need to make complete revolutions. So you need to be going 2 pi times a whole number. But that whole number can be negative so that we're taking off revolutions, meaning that you'd be going in the negative direction. And that's okay too. Okay. So if you can do a first revolution solution, and you can write 2 pi n, that's really all there is to it. Trig equations on specific domains. So here we're looking for strange domains, like if we have not a general solution, but also not just the first revolution. I got cos x equals a half, so still regular stuff here. Reference angle is going to be, there's an x value of a half, so I'm talking about pi over 3. Okay. I'm going to choose my quadrants, ASTC, cosine's positive in these two quadrants. Try and do an okay job of drawing them. Here's pi over 3, and here's pi over 3 in those two quadrants. Okay, now here's the weird thing. The solutions aren't just restricted to 0 to 2 pi. You can go up to 3 pi, which is 1.5 revolutions, because every pi is 180 degrees. Let's see all the times that we run into these solutions. Really, the solutions are just represented by the sticks on your drawing. So there's a solution at pi over 3. There's a solution right here that you run into, which would be at 2 pi minus pi over 3, or 5 pi over 3. But you're allowed to keep going in that positive direction. So you can go and go all the way around to 2 pi and keep going, because you can go up to 3 pi, which would be 1.5 revolutions. Oh my gosh, you run into this one again, which would be 2 pi plus pi over 3, or 7 pi over 3. It's actually just a coterminal buddy of this one here. It's plus 2 pi, ends up in the same place. What about if we go in the negative direction? Are we going to run into any solutions? Let's grab, I don't know, it's kind of a gross color. Let's use it anyways. We're going to run into that solution. That's negative pi over 3. And that is a coterminal buddy of the green one. It's really just subtracting 2 pi, subtracting a revolution. Now, in the negative direction, you're only allowed to go this far, so you're not going to run into another stick. In the positive direction, you're only allowed to go this far, so you're not going to run into like a fourth stick. I'm going to undo that. So there are 4 solutions. Don't try and make rules for yourself that, oh, if the domain is such and such, it's going to have this many solutions. Just look at how many times you run into those sticks. An alternate way to do this is to get a general solution and then just plug in some n values. But I think this is better. You see a picture of the solution, and you just go with the domain that you're given. Lastly, we're just putting together two things that we love, quadratics and trig equations. So to be able to do this, we do need to be able to solve some quadratics, typically by factoring. Let's see what we get. We've got 4 cos squared x minus 1 equals 0. If you can factor, I think you should. So I would consider this a difference of squares. 2 cos x plus 1 and 2 cos x minus 1 equals 0. And if you need to review some factoring, I do have a grade 10 oriented video that's on that, on your common factoring techniques. And so that gives us two different little equations to solve. It gives us this one, 2 cos x plus 1 could equal 0, or 2 cos x minus 1 could equal 0. It doubles your work having a quadratic, because quadratics can have more solutions. And when we say quadratic, we mean something that involves a squared. Okay, and each of these, though, is not difficult to solve. Like, I can move that 1 over. 2 cos x equals negative 1. Cos x equals negative a half. Over here, I'd get 2 cos x equals 1. Cos x equals a half. And I'm just going to do my regular stuff here. So the reference angle in this one's going to be an x value of a half. So the reference angle is going to be pi over 3. It's also going to be that same reference angle on this one. Okay. And we're going to have to choose quadrants. I'm going to do 2 and 3 together here. So where's cosine negative in these two quadrants? So there's a picture of my solution. And I'll finish off the left-hand side one. So one of these answers is going to be, I'll try and color code these, but it's going to take a lot of colors. It's going to be pi minus pi over 3, which would be 2 pi over 3. One of these solutions is going to be pi plus pi over 3, which would be 4 pi over 3. And those are some solutions to the initial equation. I guarantee if you plug them in, it'll work out for you. If we do the same thing over on the other, sort of half of the equation, 2 and 3 together, this one worked out with some nice symmetry. They're not always going to, though, so don't assume that. And again, we've got just our basic domain, first positive revolution, so there's no fancy domains to worry about here. So that's going to give us an answer of pi over 3. And this last one is going to be 2 pi minus pi over 3, or 5 pi over 3. All four of those answers are solutions to this quadratic trig equation in the first revolution. And finally, we have a quadratic trinomial. So for quadratic trinomial, you're going to want to make one side 0. Cos x minus 2 equals 0. Now, it's a long trinomial. You might go off and think about, well, how would I factor it if it didn't have those coses in it? It was 2n squared plus 3n minus 2. Some people are guessing checkers. Some people are decomposers with their long trinomials. It's up to you. I like to guess and check. But again, either way is fine. And this is how that one would factor. Okay. So we're going to end up here with the same thing, just with some cosines involved. So this is going to factor to 2 cos x minus 1 by cos x plus 2 equals 0. That's the equation. And if either one of those brackets are 0, then we have a solution. So let's pull this down. That would give us one of our equations is this, 2 cos x minus 1. And one of our equations that we have to solve is this, cos x plus 2 equals 0. All right, I'm going to move some things around. Cos x is a half. I'm going to talk about my reference angle. We've seen this one a lot so far, so that's pi over 3. I'm going to choose my quadrants and sketch it. So cosine is positive in these quadrants. Okay. So what does that give us as angles in standard position? The first one here is going to be pi over 3. And this one over here is going to be 2 pi minus pi over 3. We actually just solved these in the last question. They happen to be some of the elementary equations. Those are the first revolution solutions. To turn them into general solutions, no big deal. Plus 2 pi n, where n is an element of integers, or n belongs to the set of integers. All right, we've got to go to the other side. We've got to do cos x plus 2 equals 0. So that's cos x equals negative 2. And so that's clearly not going to be on the circle. And so you might be inclined to go theta ref is the inverse cosine of 2. And if you do that in your calculator, it will say error. And we're just throwing this in here to let you know that sine and cosine can only take values from negative 1 to 1. Negative 1 to 1. That's because if you imagine some point in space, the only way that you could get a sine bigger than 1 would be as if this y value was bigger than the radius itself, or the hypotenuse that you're creating. And that's impossible. Okay, so you're kind of off the hook for this half of the equation. This part over here on the right-hand side has no solution, or no roots if you prefer. But the whole quadratic itself does have some solutions, those ones that we found on the left. Okay. This does not hold true for tangent. Tangent can take values bigger than 1, but sine and cosine cannot. I hope that you found this helpful. I know it's a bit of a whirlwind tour of a lot of the concepts that we've covered, and it's not completely exhaustive. If you're looking for some practice stuff, check the PDFs in the notes. And there's also a full filled-in unit circle on the last slide. So I'll just put that there in case you want to pause and take a look at it. But generally, we're going to operate from the unit quarter circle. All right, good luck with the material, folks, and take care.